to talk to you from, I mean, while sort of this online sitting has its drawbacks, right? And we all feel that I mean, it also gives rise to these opportunities that sort of for me to talk to you without you traveling throughout the length and breadth of the country. But in the beginning, I'd like to extend sort of a warm invitation to all of you to visit the IIT Gandhinagar campus. Right, this is a picture of a this is a part of the academic area. This is nowhere close to the actual campus. We call this the Sandhya Chhaya, right? And the architecture, if you see on top, it should remind you of Gujarat's kite flying passion, right? So that's how it's designed. And I found this a particularly suitable picture for our sort of image for our talk on core sets, right? Because what the structure is and the kind of picture it sort of projects on the ground, right? Because of the sun, right? That is vaguely indicative of what we are going to do with the actual data, and we are only going to work with something which is a shadow of the actual data. So it's my poor attempt at so please come whenever you can. Okay, so just to start off, I'm going to start off with some motivation that you shouldn't really need too much convincing, right? That we all have heard about big data, right? Big data, and there are and a lot of literature, a huge amount of literature in machine learning, data mining is really geared towards how to manage these, right? In terms of all these different varieties, velocity, all the different characterizations that we do. And there are many different, and here in particular, we'll be talking about one or two. I'd say that we won't really deal with the variety part of it, right? It will mostly be about the volume part of it, the volume and the velocity, right? That the fact that we do have very large data sets, and we really need to be able to deal with it very quickly, right? So while it's I mean, we do have a lot of machines, right? And we do have very heavy GPUs, and we could of course use this. So we could throw more and more hardware at it, but it doesn't come. I mean, everything comes with a cost, right? First of all, there's of course the financial cost, right, of buying the latest and greatest big GPU, of utilizing the sort of time, of booking the time on the large supercomputer, right, or of using these Hadoop or distributed systems, etc. How do we get these, right? It's not always easy to get these, right? And secondly, there's also other costs, right? For instance, if you're sort of trying to scale up, right, from a single machine to a distributed system, right, it's not trivial to do so, right? Because the code that you run, right, for a single machine might not always be the optimal code for a distributed system. Think about the following, right? And this example I like to give in my class. Think about the simplest algorithms that we teach in algorithms course, right? For instance, think about the simplest algorithms of sorting, right? Or of finding, or anything in graphs. Let's say finding out shortest paths, finding out the minimum spanning tree, right? Is it easy to parallelize this, right? And if you think about it, it's not, right? Because if it is, let's say, finding out the shortest path, right, there is an inherent sort of bottleneck of building the solution one step at a time, right? So therefore, it's not easy to see that if you give me 10 computers instead of one, I won't necessarily be able to sort of make the code 10 times faster, because there will be an inherent bottleneck. Okay? So one thing, and this is true for any new computing system, right? If you have GPUs, right, then ensuring that your code is actually scaling up to the extent that you should, right, requires you to write smarter code, right? Requires you to learn CUDA, requires you to sort of how to distribute the work among GPUs, all of that. So basically, nothing comes for free. So here in this paper, in this talk, I'll try to propose an alternate view, right? And this is a view of, I'd like to call this a view of a lazy person, right? And this view is as follows. I mean, I'll try to go very slow. So please feel free to stop me and ask questions, because I don't want it to be just me sort of giving a talk for 1.5 hours. Please stop and ask questions. I'll try to stop myself and slow down myself, but please feel free to do so. Okay. So in this talk, I'll try to propose an alternate view. This is not a very novel view, frankly. I mean, so the novelty is how it is implemented, right? So the basic theme of it is very simple. Is that can we reduce the data, right? If I have very large data, right, and I want to use it for a specific task, is it really necessary is it really true that most of the data is useful, right? That's the question that I'm going to ask, right? And if not, right, can I quickly figure out which part of the data, which subset of the data is useful and work with that? Okay, so two things I say, right? First of all, I need to be able to quickly figure out which subset of the data is useful, right? Because if figuring out which subset of the data is useful takes a lot of time, then it is pointless, because then I might as well work with the full data. Secondly, right, when I throw away data, I want to do it in an intelligent manner. Throw away or select. When I select data, I want to do it in an intelligent manner. What do I mean by that, right? I mean, it's that I should not, I mean, something like this, right? Somebody gives me a sort of, I'll give very simple examples. Somebody gives me a file in which, think about a text file in which every line is a training example for a classification. Can I just take the first 10 MB of the file and work with that if the file is 100 gigabyte? Possibly not, right? I mean, because in the first 10 MB, the lines that we'll consider will likely not have representation from even all the classes, right? And even if it has a representation of all the classes, right, it might not be a good enough representation. It's possible that, okay, most of the, out of the 9 MB and the corresponding lines in the file, out of the 10 MB I picked, the first 9 MB is one class and the remaining 1 MB is another class. It's possible that there's some kind of bias, right, in the ordering of the file, right? So then think about the next step. What is the next obvious solution? See, when we propose solutions, we should always build from the obvious and then go towards smarter ones, because we need to understand why are we proposing trying to think about smarter solutions, right? I mean, apart from the fact that I need to do something to get my salary. Okay? So what is the next proposed solution? I'd say that the next proposed solution perhaps is that, well, we all know about uniform sampling. Why don't we sample uniformly and then do something, right? Perhaps, perhaps not. So this is a harder question, right? This is not obvious. How do I figure out, right, which data is useful, what part of the data is useful, and how do I pick this? So then the other question I left unanswered here: does uniformly picking work? And if it works, then why am I giving a 1 hour talk about this? This is what I'll talk to you about. That not always, right? And there are smarter ways of doing this. So here is the basic roadmap, right, of what I'll talk about. What I'll talk about, right, is that I'll talk about two running examples of machine learning jobs. One is a clustering, right? And while I will mention results about many different clustering, the one thing to keep in the back of your head is always k-means clustering. Because that is, I picked that example because that is something all of us are familiar with. And the other example I'll talk about is regression, right? Again, I could have picked regression, classification, or I mean a bunch of these examples, right? I mean, but again, I mean, going along the lines of that, picking the example that most of us are familiar with, I have picked the example of linear regression, right? Because that is one of the first things we teach in our class, right? And what I want to say is that look, right, that if I'm faced with these problems, k-means clustering and a linear regression, and I'm really talking about very large data sets, right? What does it mean, right? I mean, so first of all, what does large mean? Okay. In fact, there's, I mean, I'll probably blabber a little. So what is the definition of big data, right? What is big, right? And of course, you won't be surprised to hear that this definition has kept on changing, right, with the amount of resources that we have, right? I think there's a very famous quote from, I don't know, perhaps Bill Gates himself, who said that, okay, who in the world needs more than 25 megabytes of memory? 25 megabytes of data nobody needs more than that. Right? So that has now become a very famous meme. Okay, and similarly, I mean, now that our systems are changing, what do I mean by big? And then wow, when do I need these examples? Right? My rule of thumb is the following. My rule of thumb is that to you, right, the definition of big is individual to every system. Right? My rule of thumb is the following, that if the data that you're working with, right, you cannot fit into your computer's memory, right, then we will call it, right, something on which we want to apply these techniques. Then we will call it big data and something on which we'll apply these techniques. Right? So the data does not fit in my computer's memory. Period. That's my simple definition of it. Why this definition? Well, if you think about it, right, this definition makes sense, right? Because most of the algorithms in our undergraduate algorithms class and the introductory machine learning class that we talk about, then when we talk about the computational complexity, how much time does it take? Right? We always assume that the data is in memory. When we say that sorting takes n log n, right, we are counting the number of comparison operations. We're not really counting how much time it takes to fetch the data from disk to memory. We're not really, because we're assuming that the data is in memory. Similarly, all problems that we have analyzed mostly, right, unless you take the second or third level algorithms clause, really calculates the complexity of the problem, assuming the data is in memory. Right? However, as you well know, that's not necessarily the issue. That's not necessarily the best thing to do. Let me just throw out, I don't know if you, I guess everybody can answer questions. Everybody would be able to speak. So my question is the following. So if I ask you, how do you relate, right? Let's say memory access time versus disk access time. Okay. So possibly a hard disk. I'm not talking about a SSD. So SSD is slightly less. So what factor? How do these two things relate? Memory access time versus disk access time. Any thoughts? Factor of 2, factor of 5, factor of 10. Any suggestions?
Participants can raise their hands if they want to answer this question.
Oh, acha. I didn't know that technology. So they won't be able to speak directly?
No, sir. They can raise their hands and we will unmute them.
Oh, acha. Okay. Sure.
Yes, Om. Om, sir, please unmute yourself.
More than 1,000 times.
More than 1,000. So basically that's correct, Om. Thank you. So the disk access time is a factor of more than 1,000, right? More than the memory access time. Okay, and that is very significant, right? So what we will try to do is the following, right? What we will try our goal in these examples, right, is that you assume that you're given a data set which you're not able to fit in memory, but you have to run k-means clustering or regression or classification on this, right? And all of these algorithms need to take multiple passes over the data. So most of the time will actually go in accessing the disk. What our goal will be, right, to reduce the data set in a smart way so that we're able to fit it into memory. Plus, it will come with nice properties. So the reduction will come with very nice properties that will say that, okay, if you calculate the solution only on this small data set, right, you will have a solution that is as good as the solution that you would have obtained by working on the full data. Okay. So the solution that is calculated by working on the small data would be almost as good as the solution that's obtained by working on the full data. So there are a couple of things I left vague out here. What do you mean by the solution as good as? What measures the goodness of the solution? Number one. What do I mean by almost? So all of this. So these definitions will change based on the problem that we are solving. Right? When we are solving regression or classification, the quality of the solution will of course be measured by the accuracy, by the quality of the fit, linear regression fit. When we are doing clustering, right, the quality of the solution will be measured by the k-means objective function, right, if you are doing k-means clustering. So that will change. However, our properties, the properties that we stated won't change. And when we said almost, I'll define what almost means. So what we will do is that we will talk about a few approaches to do this. The first approach will be utilizing geometry. The next approach will be using something more statistical, basically sampling, but not uniform sampling. What we call importance sampling, right? Basically what we'll figure out is that which data points are more important than the other ones. Right? And then we will talk about I'll just give some, pointers to course sets for other machine learning problems. So I'll go through it, but we won't go through it in much details because this is a very vast literature. Then what we will see is something very funny, right? What we will see is a very interesting setup, right, called the streaming setup. Okay, and you probably know what a stream. You might have heard about the streaming setup. The streaming setup means that you're not really allowed to store your data, right? Imagine the following. Imagine that imagine that you are sort of barging into an office, going into an office, right? And there's a huge disk of data in there, right? But all you have to process the data. Imagine yourself a hacker. All you have to process the data is your cell phone. Cell phone has like what, 8? If it's a good cell phone, 8 GB of memory. The data is 160 GB, right? And again, you can go over the data. You can process the data through your cell phone, pass the data through your cell phone. You can read through the file, right? But you cannot store anything because the cell phone has only 8 GB of memory, right? So you cannot, 8 GB of total memory plus anything, right? So this is called a streaming setup, right? And this is very common. For instance, if you imagine that you're coding for all these routers, for all these network switches, right? They see a huge amount of data and they have to do analytics on that data, right? They have to figure out what is the denial of defense attack, etc., but they cannot really store it, right? This is called a streaming setup. Okay. What we will see is that the techniques that we see in the first part, how they will give us very nice algorithms for the streaming setup. Okay, and then we won't really talk about lower bounds, and then we will see some other very interesting applications of these techniques that we saw. Right, we will talk about some applications to compressing neural networks. Right, we'll talk about some applications in dataset privacy. Right, and again, these applications, I'll just tell you pointers and what the results are. I won't go into much details of it because we don't have that much time. Okay, so if there are no more questions, any questions? Perhaps if there's a chat also, I don't know.
Sir, actually the chat has been disabled for the attendees. Participants can raise their hands if they want to ask any questions.
Sure. So then my invitation would be at any point, please raise your hand and please feel free to interrupt me. Okay. So now what we are saying is the following, that now we are going into a little bit of definitions. So we'll call these subsamples, the selected data sets, to be core sets. This is a standard literature, standard name, right? And the notation is the following. I'll try to sort of go as little on equations as follow. So we'll call D to be the full data, so the full data, right? And now there is an algorithm on the full data that works on the full data and that gives me the answer, right? So what is the answer? Well, the answer could be depending on what you're interested in. The answer could be learning a model, the model that you learned, or the solution to the k-means problem, the solution to the k-means clustering. The answer could be a clustering, it could be a regression model, it could be a classification model. That is the answer. Right? So the algorithm processes this and gives me the answer. Okay. The question is, now we're asking is the following: can we find, right, a much smaller part of the data, and this is what we are calling C, right, such that the performance of A on C and the performance of A and D are very similar. Right? And most of the time that we will consider that C is actually a subset. Although I should warn you that sometimes, I'll give you examples, sometimes C will not be a subset of the original data. I will have to create C in some other smart way. And the other property that I want is that the size of C must be much less than the size of D. That's the motivation that I say, that keep in mind that D does not fit in memory. I'll have to make C so that it fits in memory. And why is this useful? Well, obviously, right? Because if you are able to do this with this guarantee and with this guarantee, right? Then suppose algorithm A takes times takes times order, I don't know, n cube, right? So initially, so to calculate this exact value, you would have needed order d cube, whereas to calculate this value, you would need order c cube. And if c is much smaller than d, of course, c cube is much smaller than d cube. Right? And we have this guarantee that you have a very close solution. Right? Sometimes that is enough, right? Because in most of the data mining, data analysis questions, right, you don't really need an exact solution. So this is why this is useful, and we'll come to it. We'll come to more. So I'll start with simple examples, right? And the simplest example, right, is the following: that suppose you're solving a linear system. Right? So this is an actual exact linear system. So it will tell me, why is this person wasting our time? We all know how to solve linear systems. So but this is over-constrained linear system, but it's solvable. So we have a matrix A. Sorry, this is a matrix A, and this is the target B, and you're trying to find X. Right? You're trying to solve AX equal to B. And suppose I've told you that this is solvable for now. Okay. And just for notation, we call this n and we call this d, right? So n is the number of constraints or data points, right? And d is the number of features. Basically, x is of dimension d and b is of dimension n. Okay, so ax equal to b. Okay, so we all know this is an exact solution. We all know how to solve it. And over constrained but consistent linear systems, we know that there's a closed form solution. Right, which is that you get x by, I mean, we all know how to solve it using Gaussian elimination, etc. But you can write down the closed form system by calculating A transpose A inverse A transpose B. Okay, this is what is there. What is the smart thing about this? There's nothing. This was discovered in about 1800s, about 200 years from now before. So what is it? So the interesting part is the following, right? Let us see how much time this takes. Okay. So I'll say that calculating, I mean, I'll tell you without sort of going into it that calculating this, right, takes time order nd square. Right? We won't go into the details of it, but it should be easy for you to see that calculating A transpose A itself takes time nd square. Calculating inverse of it, it's a d by d matrix. Calculating inverse of it takes time d cube. So this times nd square plus d cube. Right? And we have said that n is bigger than d. So I'm writing this as nd square. Okay. So now the question is that, can you do it smarter? Do you really need to keep this entire matrix A into memory to calculate A transpose A, and specifically A transpose A inverse? Okay. Turns out no, right? Because see, what you're really interested in is this particular problem, solving this particular problem. Turns out you can do the following, right? In fact, let me do a different color. Perhaps might be going a little slow, but that's okay. Suppose you pick out, right, the linearly independent columns from A. Right? So these are the linearly independent columns. Because see, A has n linearly independent rows, because A has n rows, so therefore not all of them are linearly independent. So pick out d linearly independent rows from A. So and call this A tilde, this matrix A tilde, right? So now, I mean, you can do a little bit of calculation to see that A transpose A tilde inverse A transpose A tilde transpose, right, is exactly equal to A transpose A inverse A transpose. Sorry, A transpose A. Yeah. I should have. So this remains A. This remains A, but this becomes A tilde. So these two are exactly equal, as long as A tilde are linearly independent rows. Right? It's a very easy calculation, but you can do that to see. But but then you'll say that, okay, then why do I work with this n by d? Why don't I work with the d by d matrix out here? Right? But see, how do you get the d by d matrix? How from this n by d matrix? How do you get the d by d matrix? Yeah.
Excuse me, sir. Sir, can I take the liberty to unmute participants from time to time because they have been busy?
Yes.
Okay, thank you, sir. Okay.
Yeah.
Subrat Mukherjee, please unmute yourself and ask your query. Siddharth? Yes, Subrat.
So how
Please ask your question.
selecting the A tilde from the A matrix?
So that's the question, precisely. Very good question. So how do I select A tilde from the A matrix? See, you have heard about Gaussian elimination, right? So, so techniques are like Gaussian. I mean, it's like saying that think about the n rows as the n vectors, right? And we want to select linearly independent vectors. Okay. So out of n vectors, I want to select b that are linearly independent, right? So basically this is, I mean, you can do many different things, many different names for it. You can calculate a QR decomposition and take the R. You can, or you can just apply Gaussian elimination on the rows, right? And then you'll basically get the independent rows, and everything else will become 0, right? So that's a short answer. The question
Actually,
is
sir,
that,
I was asking about the means practical approach. If we are having a huge data set, then how we are getting
very
that?
good question. That is the, so for that, hold on to your breath, because all the techniques that I described, right? See, this is the time it takes to solve the to solve the linear equation, right? But in order to pick A tilde itself, it takes the same amount of time. Okay, so
Yes,
so this is basically saying that I give you a shortcut, but the time it takes you to take the shortcut is the time it takes you to drive to take the full road. So this is useless, right? So so what I'll tell you is that is how to pick these rows, right, in much faster way. That's what we will tell you, right? And in fact, what I'll outline to you is that how to pick these rows in time that is proportional. So this is a notation that I'll use in time which is proportional to basically reading the matrix. Just in time that is linearly proportional to reading the matrix. This notation means the number of non-zeros in the matrix, NNZ of A. So if the matrix is sparse, then this is small. So in time that is proportional to the number of non-zeros of A, I should be able to pick the rows. That's what I'll show you. Okay? We won't go into the details of it. I'll just show you that this is possible. Okay. So in fact, we'll show you for a harder problem. Okay. And here the problem is that we have an over-constrained system, but now it is not exactly solvable. Right? It is over-constrained system, but we're not guaranteed it's solvable. And you know that that this is the difference between linear equations and linear regression. Solving a linear system and a linear regression. That now we are trying to find the x. So this is A. We're trying to find the x that minimizes ax minus b. So finding out the best fit in some sense. Right, and this will be like either a 2 norm or a 1 norm or some other norm, some p not equal to 1, 2, because this is a vector. This is ax minus b is a vector, right? So now the question is the following, right? If I had promised to you that I'll be able to sort of solve it quickly for linear systems, can I apply similar techniques, right, to actually pick these smaller data sets, right, smaller A tilde, right? For these problems, for these general problems, for these linear regression, these regression problems, and yes, you'll be able to do this. Right? It of course gets a little more complicated. So p equal to 2 is easy. We'll talk about the p equal to 2 case. P equal to 1 is a little harder. General p norm is a lot harder, but it's possible, right? And we can find this efficiently. Efficiently means we can find it in time which is smaller than time that is needed to solve the full problem. This is what we'll show. Okay, so yes, for different LP norms. So I just write down what LP norms are. So the LP, I mean, just for notation, the 1 by sorry, I should have written. So summation xi absolute value to the p I equal to 1 to n to the power 1 by p. So this is what I mean as the LP norm. P equal to 2 is a standard Euclidean norm that I mean. P equal to 1 is the L1 norm. Okay. The next problem that we'll talk about is clustering, right? And specifically think about k-means clustering. What is the problem there? Problem there is that we're given these points, right? And we have to find out, okay, that here are 2 centers. So think about k equal to 2 here, right? So now the question is that where should I put these 2 centers, right? So that the cost is minimized, and the cost is measured by assigning everybody to their closest center, right? And then you sum up the and then you do something to aggregate the costs. Okay. So where should I put the two centers? Should I put center 1 here, center 2 here? Should I put center 1 here? Should I put center 2 here? Right? Where should I put the centers? That's what we'll try to minimize. And here is what we will do here. What we will do is that instead of the original data, we'll select some of these original data points. Perhaps we'll select this one. This one comes here. This one comes perhaps, I don't know, this one comes here, right? And we will add weights to these original data points. Think about that they're small sort of points out here, and that's what the size of the balloon out here indicates the weight that we give. Basically, this one data point will capture a bunch of data points out here. This one data point, for instance, captures these two out here. So that's why it has a weight. What we will say is that solving the k-means problem in this setup, right? By solving the k-means problem in this setup, you can figure out centers such that you can use the centers in the original data. You can use them in the original data, and you will get a cost which is very close to the best cost that you would be able to get. Okay. So I'll solve the problem on the smaller data set. I'll take the solution. Right? See, the solution is basically the two centers. I'll take the solution. I'll evaluate the value of the solution on the full data. And we will be able to say that, okay, this is a very good solution. It's perhaps not the best, right? But it's 99% close to the best. That's the kind of statement that we will make. Okay. So I hope that's okay. So let me now then sort of formalize this a little bit. And here is where we'll need a little bit of sort of notation. Yes. Questions? No?
Hello, sir.
Yeah.
Sir, on what basis we can select the weights here?
On what?
Means how we can select the weights on the basis of X.
We'll come to it. We'll come to it. How the weights will come. How the weights will. So okay. Intuitively, so think about the following. Intuitively, the weights will come because if I aggregate these two data points, right? So that they are represented by a single data point out here, the weight will capture the fact that there are two data points that this captures. The weight will be 2. That's a very high level way of doing it. Right? But exact ways. Yeah. It's like so if you are selecting councillors for your districts, the weight of the councillor is the number of people in their district, right? So it's kind of like that. I don't know. That's very so okay. So I'll need a little bit of formal notation. Okay. Okay, so because I want to capture all of these problems in the same framework. Okay, so what we will say is that we are trying to solve an optimization problem. Okay, I'll tell you what and this optimization problem can be regression, can be clustering. So we will denote Q as the proposed solution to the optimization problem. Okay? And if you look at the literature, they call these queries. So if you're solving a regression problem, the queries or a classification problem, the query would be the vector x. Remember, we were trying to solve ax minus b, right? Now, and x is the query. So x is the query. So a and b are the input, right? When we are trying to solve clustering, the query is the location of the k center, c1, c2, ck, because that is unknown. Intuitively, query is the unknown, the model that you're trying to find. Okay, and our task is to find out what is by going over all the possible queries in a smart way, right? What is the best solution? What is the best model that fits this data? Query is model, basically. Okay. What is the cost? So for every query, there's a cost that is defined. So I write down the cost as f of q, as the cost of the query q. Okay. So for the let me talk about the k-means setup. In the k-means setup, we have the points, right? And the query is the two centers, C1 and C2. So the cost of C1 and C2 of this query is basically the assigning everybody to the closest center, right? And in the k-means clustering, and then you sum up all the costs, right? This is the k-means clustering cost, right? What we will say, right, is that the total cost of the query for any query can be represented as an aggregation of the costs by individual data points. Okay, what is this aggregation? See, look at the k-means query. Okay? These I've written D to be the distance of x1 to C1. Right? You basically take the distance of every point to its closest center, and this is the notation that I've used. So square the distance and sum it over all the points. This is exactly the problem of k-means clustering. If you are thinking about k-center clustering, it's very similar, right? You take the distance, of everybody to their closest center, right? And then take the max of the distances instead of the sum. So the only difference is that the sum versus the max. Okay, that's the only difference between k-means clustering and k-center clustering. Okay, so all other clustering, all clusterings, almost all, I should not say all, almost all clusterings, you can represent it this way, right? That basically you sort of do the cluster, right, and then you calculate the cost of every point for this clustering that you do, sum up all the costs, take the max of the costs, do some combination of the costs for all the points. So this is my function f, capital F, right? Okay, so and for regression, what is the regression? Again, the regression is also easy because so if you look at AQ minus B, 2 norm square, this you can write it as sum over all the rows AI transpose Q minus BI 2 norm square. Right? Basically, you calculate. Q the query is now the model, the fit. So the coefficients that you're learning, right? And basically you calculate the loss for every data point. So AI is the data point, BI is its target. Calculate the loss for every data point and square the loss and sum up. So that's the least square regression. Okay. So what we will use is that we will use this general aggregation framework to now capture bunch of different examples. Okay, so we will I sort of jumped ahead. For instance, in clustering, right? We say that okay, we propose 2 centers, right? This is my Q, right? Now you calculate the cost and then you assign to everybody. Right? Oh, sorry, there's some weird animation. So we will write down f of q to be equal to sum over all I, some function f of xi of q. So xi is the ith data point. Right? So the total contribution of all the data points and then according to that. Okay. So this f can be the distance of xi to q. This f can be something. Sometimes the sum will also be a max, right? Or some other combination way of combining. But we'll mostly be dealing with sum in this talk because that's easier to deal with. Right? So now what is the strong course set? So this is see here we are combining by sum. Here we are combining by sum. Here we are combining by max. Here the function f that we're talking about, right, is AI transpose B minus Q. This is the function f of AI BI Q. Right, this is the loss function. Basically, it's the loss function for the ith point. Okay. So now, what is the definition of a strong course set? Let me erase. Erase this. Okay. I'm not sure how to erase this, but anyway, it is already okay. So now we're defining what is a strong course set. Now we are giving a formal definition. What we will say is that suppose we have the original data point and suppose we have Q, which is proposed solution. Remember, keep in your mind, proposed solution is basically k-means center for k-means, the model for classification. These are all the proposed solution. So the total cost for this proposed solution we are presenting as an aggregation over the point-wise costs. A course set is a set of points and their corresponding weights. I don't know how it came, but we'll come to it. Right? The course set cost of the solution of the proposed solution Q is this particular quantity. Capital F, the same loss function, but the data set changed from D to C, but the query remains the same. Right? And this is calculated as basically you calculate the point-wise cost of xi for this query Q, multiplied by wi, and then sum it over all I. Okay? This is the definition of the way of the cost of the query Q on the set C. and we are multiplying by wi because the points are weighted. So think about the fact, I mean, weights, you should think about that at this location, there are this many points, wi copies of this point. That's why we are multiplying by wi. Okay. Now, I mean, again, so this is we are saying that f of q is equal to summation of f of xi q, summation over I. For k-medians means, we have gone over this. I'm just reiterating it. F of xi q is the square distance of xi to the nearest center for the query q. This should have been a small q. For the linear regression, the pth norm linear regression now, right? Now f of xi q is the ai transpose is the loss of the ith point, right? According to this pth norm. Many optimization problems can be captured in this generic setup. Now what I want to say, right, is the following. I want you to give me a set C. So I call a set C to be a strong coarse set if it has the following property. This is important. I want you to say that for all possible queries Q, if you evaluate Q on the full data, so this is basically Q evaluated on the full data, right? Versus if you evaluate Q on the coarse set C, right? The two lie within a very close factor of each other. So think about epsilon to be epsilon, choose any epsilon, right? So think about that. I mean, epsilon is like your hyperparameter, is your user defined parameter. If you said, oh, okay, I want to work with epsilon equal to 0.1, you should set that to be the value of epsilon. It's a user specified parameter. And what you want to say, so the use of this parameter will go into the construction of C, right? And what you should be able to guarantee is that for all possible queries Q, right, you should be able to say that, okay, whether you evaluate this solution Q, this model Q, or the K centers Q on the full data or on the coarse set, it gives basically the very same value. Values within, I mean, within 99% to 101% of each other. Okay. There is also another caveat. We won't go too much into it. And the fact that there is another user-defined parameter is that these are what are known as randomized algorithms, right? This is with there is a failure probability for it, right? And this statement will hold with 1 minus the failure probability. The failure probability also is again something that you are free to set. If you say that, okay, the probability of climate change sort of flooding sort of BHU tomorrow is 0.0001. So therefore, and if that happens, I don't care what your solution is, right? So that's your failure probability, 0.0001. And in all other cases, I want this to happen. So with probability 1 minus 0.9999, I want to make sure that this happens, right? So both the construction of C will take into account both the C and the delta, right? These two probabilities, okay? And will kind of ensure that this happens for all possible queries Q. Now again, my question to you is, and please sort of unmute. My question to the audience is that why is this important? What would this help us do? If I'm able to create such a C, why would this be important? Any thoughts?
Participants can raise their hands if they want to answer this question.
Thoughts? Why am I giving such a weird statement? It's something like this, right? It's something like this that I'm telling you that look, it's something like, so you've all sort of seen all these sample surveys, these exit polls, right? It's something like saying that, okay, that for every, so think of Q as every candidate for whom people voted. That, I mean, it's something like saying that the exit poll is good, strong coarse set, if for every candidate, the vote that the candidate gets by counting all the votes versus the vote that candidate gets right, by looking at the exit pole is within a factor 1 plus minus epsilon. What does that allow us to do? Okay, in the interest of time, I'll say that basically allows us to use the exit poll to say who is likely to win, right? If everybody's vote count, if I'm assured that everybody's vote count I have estimated very well, right? By looking at the who wins in exit poll, I can basically be reasonably confident to say that this person will win in the actual election. Exactly the same thing, right? If that happens, right, then by optimizing by finding out the queue that performs the best according to FCQ, right, I'll be able to say that which queue will perform that same queue will be close to the optimal when I consider the full data. It's basically the same thing. Okay, so the above property I'll show you formally will help us go to a close to optimal solution by using C itself. I can now throw out the rest of the data. Okay, so one warning bell that should kind of occur to you is that what are we talking about all possible queries queue, right? This is a tricky statement because if you remember, so what is a query? A query is a model. A query is a k centers, and there are infinite number of these queries. In fact, there are uncountably infinite number of these queries. So how can I do this? How is this even possible? That is not clear. In fact, this is possible, right? This is possible. This is possible in a very, very smart way. And this is the smart way that is actually, I mean, we talk about it in the algorithm set. So if you are interested in machine learning, this is actually at the heart of, also at the heart of what is known as learning theory, right? And it has been discovered simultaneously, independently by the algorithms people, by the machine learning people, and it's very connected, right? So, but anyway, we won't go into the details of it. Okay, but this is possible to say this for all possible queries queues simultaneously. And okay, so now let me formalize this statement. As I said, the above property helps us to get to a close to optimal solution using C. Why is that? So suppose Q star is the optimal solution calculated on the full data D. No. So think about the k-means optimal k-means solution. Always keep one of the concrete examples in your mind. So Q tilde is the optimal solution using the course set C. Basically, the k-means solution is in the course set C. And now we have the following guarantees. We have that C is a strong course set. This is when we call C to be a strong course set. Now, because C is a strong course set, right? And we said that for all Q, I'll just write the notation for all Q, f of Q of C. So I'll write this in this way instead of writing just for the interest of time, f of Q on the full data. So there is implicit D out here. Okay. So because of this, I can say that f Q star C is within 1 minus epsilon, 1 over 1 minus epsilon of f Q star calculated on the full data. You just plug in Q equal to Q star. So from this itself, I get it. Now, I can also say that because Q tilde is optimal on the course set and Q star is optimal on the, not the optimal on the course set, f of Q tilde of C is less than equal to f of Q star on C. So because Q tilde is best solution on C. Okay. And Q star may not be the best solution of C, so therefore this is the case. Again, by applying this property for Q equal to Q tilde, we get this third equation, right? F of Q tilde on the full data is not more than 1 plus epsilon f of Q tilde of C. Now, if you string these three together, right, it's a little bit of algebra that shows that f of Q tilde, right, is within 1 plus epsilon by 1 minus epsilon of f of Q star, right? So plug in epsilon equal to 0.01. So it says that f of Q tilde on the full data, see here we are calculating on the full data, is within 101 by 99 of f of Q star on the full data. See, what is this? This is very interesting. I mean, 101 by 99 is very close to 1, right? It's like possibly like it's like 1.02 or something, or 1.03 f of q star on D, right? Which means that while I don't have the optimal, but see this q tilde was obtained only by optimizing the on the C. And while I don't have the optimal, I have something within 2% of the optimal. Because I chose epsilon equal to 0.01, within 2% or 3%. I don't know, 101 by 99 might be equal to 1.03. I don't know exactly. Okay. Okay. So this is why we want this. Yeah. I can hear.
Hello, sir.
Yeah. Please.
Sir, is it so? It is basically giving the base solution which is nearer to the what we call the means. Here the Q star is giving the base solution for the C.
So Q tilde. So Q star is optimal on the full data. Getting this is expensive. This is expensive to get. Right? Q tilde is giving me a solution on the course set, and the point that you're making, you're absolutely correct. It is giving me a solution which is very close to Q star. Absolutely correct. Okay. I mean, just for the sake of covering everything. Okay. Oh wow, I'm almost an hour. Okay, I should really speed up. So related but not exactly the same is something called sketching, right? And something in which you create a randomized summary of the data, but the point is that the summary, they don't contain the original data points. They will contain linear combinations or something of the data, etc. And it supports, but it has some other nice properties. Other examples include something called property testing, right? In which we answer the questions about the data in sublinear time, but you're not allowed to look at the full data. But they're not really the same. Okay. So let's do at least a couple of only half an hour. How to create this fast cut approach, right? I don't know if we'll be able to cover both k-means and linear regression. Let's do k-means. What if we do uniform sampling, right? And because I promised you uniform sampling works. So suppose we have this. This is my example that I have. So I have log n points in here. I have n minus log n points in here, and suppose n is very large. So think of n as like, I mean, I don't know, 10 to the power 10, right? And so log n is like 10, right? Something like 20, yeah, depending on what base you take. So now in here, can I use uniform sampling to create a good representation of the data? The answer is no, because these points create a cluster which is very far off from this cluster, right? However, right, these points are very, I mean, the number of points out here is very small, right? And so if you do uniform sampling, right, I mean, you're trying to, here there is 10 to the 10 minus 10 points, and here there is 10 points. If you do uniform sampling, that unless you choose something of the order of 10 to the 10 points, you won't see a point from here at all. Right? You won't basically see any point from the second cluster, because the second cluster is very small, right? Although it might actually be very far off from the actual data, from the rest of the data. So uniform sampling does not really work out here, right? Because I mean, all you will do is that you will take the bigger cluster and you will solve the course set problem on the bigger cluster, and that solution will always put two centers. If you're solving for k equal to 2 centers out here, and so these points will have to be assigned to these centers which are very far from its original. Uniform sampling does very badly. So what can we do? Let us take another problem, the linear regression, right? Or linear regression. Can I do uniform sampling here? And I'll give you another example to show that no, it cannot. That suppose you have a matrix A which basically looks like follows, and this is a toy matrix that gives an example which looks as follows. That there are n minus d rows, this is n minus d rows which are all the same. So these rows are all the same, right? And there are d rows that are identical to each other, right? There are n minus d rows which are copies to one another. Now, if you do uniform sampling to pick rows, you will basically again. So supposing n is again of the order of 10 to the 10 and d is again of the order of 1000, right? So if you do uniform sampling to pick the rows, again you will only pick rows from here. You won't see anything from here at all, because the size of this identity is very small. It's only 1000 by 1000, right? So for any b, I mean, and then because of this identity matrix out here, it is not hard to show that for any b, right? You can actually, for any target vector B, you can actually solve this exactly, Ax minus B equal to 0. However, right, if the number of uniform samples is less than n by d, in that case, the solution obtained from the coarse set based solution, right, will not give 0 for any b. It will give a non-zero value. And because you're trying to, I mean, and therefore you cannot have the solution. I mean, and therefore you cannot get a strong coarse set kind of a guarantee, right? Because you are only you're throwing away the important part of the data, which is identity, which although it is small in size, it's actually an important part of the data. So here is the main approaches that we'll see. So first is geometric decomposition, right? And next will be important sampling, as I mentioned, right? And we won't go into the third one at all. So the first one, geometric decomposition. Let us deal with a very small, I mean, a very simple setup, because I mean, see, the entire point is to give you some intuitions so that you can follow up on your own. Suppose the points are on a line. Points are on a line. They might be high dimension, but they're all line a line. And what we'll do is the following. The coarse set for the K median, we will group the points. We will group the points into small clusters, right? And what we will do is that we will maintain one representative from every group. We will perhaps keep the average of every group. Right? And because the number of groups will be less than the number of original data points, I will have reduced the number of data points. Two questions, right? How many groups do I create, and how do I group it? Right? For instance, can I just group this point with this point? Can I create? Is this a valid group? Right? Can I group? Should I be grouping all these points together? How do I know? What is the group? Right? And this is where the smartness of the grouping comes in. Right? Because what we kind of want, right, is the following. What we will do is that we will create kind of a sort of something that is fairly close to the optimal solution. Right? We will create something which is moderately close. Right? And then we will use that, and let's say that the value of that solution, that moderately close good solution, is opt k. Right? Opt k. And what we will do is that we will create the groups based on this opt k. Right? So that we will create the groups so that the total cost by of all the groups, right, is less than epsilon k. Because see, when you're grouping, you're representing multiple points by one. So there's some kind of a quantization cost, so to say. And the way and the idea is the following: that if you have some idea of what the optimal solution is, then you ensure that the size of every group is such that the cost due to the quantization of the group is basically epsilon times this approximation of the best solution. Okay, is less than or equal to epsilon by k times opt of k, right? So the steps are that you need to get an approximation to the optimum. Some bad approximation is okay, and based on that you create the size, create the groups. So, but this is only for one dimension. What do I do for multiple dimensions? Basically very similar. What you do, right, is the following, right? Either you represent, either you draw. Let's say that you imagine that the points lie on this three-dimensional sphere. What you do is that you draw a lot of these lines. It's like you're cutting a pizza. You cut a pizza with these lines, right? And you sort of project each point onto its closest line. Project each point onto its closest line, right? And then solve the one-dimensional problem. And take this one-dimensional construction that you did, this one-dimensional coarse set, and take the union of those. Okay, and that is the result given by these people, and they kind of say that okay, if the dimension is d, right, then the number of coarse set points that you get is like k square by epsilon to the d, where epsilon is your error parameter. So therefore, if k square by epsilon to the d is less than n is the original number of data points, in that case this is okay. So in this case, so this is okay in the sense that if dimension is not too big, right? Possibly, if you're working with 1 million points, dimension, this only works, this construction only works when dimension is less than, let's say, 10, right, or 5, right? In that case, you can build this one-dimensional course set, and then you can sort of do this. Can I do this? Can I do any better? Well, let me not sort of talk about this here because this is too complicated. Okay. So we can do better in terms of what is known as importance sampling. That is the next set of sort of techniques, the more modern set of techniques, so to say. What we will do is the following. We will come out with a definition of importance, right? Some way of smartly calculating the importance of every data point, right? And based on this, we will say that, let's say, Pi be the probability of sampling the ith data point. Okay, and now what we will say is that, okay, that if the ith data point is being sampled, then I will scale it with this weight. This is the weight. Okay, so some person was asking that what is the weight? The weight will come. The weight of the data point will come on how likely basically on how we are so the weight of the data point, the way in the course set comes by the course set construction. In the case where we are creating the course set by aggregating the data points, the weight basically reflects that this one data point, how many data points it's capturing. That's how the weight reflects. In the case the course set is captured by the importance sampling, it basically reflects that, okay, that if you sampled it with probability P, the weight is basically like 1 by Pi. 1 by Pi. Right? I mean, actually, I should not really say this. Let us say that. Let me define the. If the data point is sampled by with probability P, the weight is 1 by Pi. Let's just say that, right? So that the expectation of the weight and the contribution of the FIQ, right, is this is Qi times 1 by Pi times 1 by Pi times F of AIQ if I sampled, plus 1 minus Pi times 0. Data point is not sampled, right? So basically, you can think about it as the purpose of the weight is to, and this Pi cancels out, is to make the expectation to be an unbiased estimator. That's all. Expectation of the course set should be an unbiased estimator of the solution calculated from the full data. Okay, so the important question I left unanswered: how do you design the sampling probabilities? Okay, and this is where. So again, I don't want to go into the formula of this. I want to show you the intuition behind this, right? So see, so the importance, so SI is basically the importance of the sensitivity, right? So read this one. So the sensitivity of a data point is basically that how much relative importance does it have in the worst case, right? For instance, see, this is the F of Q, right? Basically, this if you propose a solution, right? I mean, this is the cost of the solution on the full data, and this is the cost of this is the contribution of the ith point to this F of Q, right? And so the solution, the importance of the point Q, importance of the point I will be like how much contribution does it have, right, to the overall solution for the worst possible query. That's what I want to figure out. It's like saying like this. Let me give you a very sort of English example in English. That suppose I ask you, I take all of you, 175 or 152 of you, right, and I have 10 different tasks for you. One of the tasks is to draw a picture. One of the tasks is to draw is to build a sort of computer. One of the tasks is to write a program. 10 different tasks. Okay, these are the 10 different queries. And how I will evaluate you? I will take how everybody does on the task Q. Let's say that the task Q is drawing a picture. I will say that, okay, I will give a score to everybody for the task Q, and I will sum up these scores, right? Okay, so the person now what I want you to say is that which of you, right, the sensitivity of each one of you is that what is your contribution on the total to the total score for any particular task. let's say one of you, right, is like draws a picture like I don't know, like Nandalal Bose or Leonardo da Vinci, right? And so that person's contribution to the total score for the task of drawing pictures will be the highest. So your sensitivity, right, will reflect that. But it might not be so, that person might not be so good in writing a program. It does not matter, right? So because you are doing, you are really important for the query of drawing a picture. So your sensitivity will be high. Similarly, one other person might not be good in sort of drawing a picture, but they might be an amazing programmer, right? Like Bill Gates, okay? And so I will say, and so your sensitivity will be high because for that particular task, your score will form a major contribution of everybody's score for the program writing task, and so your sensitivity will reflect that. Okay, so the question is that now if I can sort of calculate every point sensitivity over all the possible queries, that forms a very nice definition of importance scores, and this is known as importance sampling. Okay. And these people have a very beautiful theorem, very beautiful set of results that says that that if I can calculate this importance score for everybody, they form a very nice way of sampling. Why will this work? I mean, again, I will give you the intuition behind mathematics. I will not show you the mathematics. Basically, that if you look at this quantity, this is a random quantity because of sampling. This is a random variable because C is random, right? And what the sampling scores that I mentioned says that choosing the sampling scores minimizes the variance of this particular random quantity. Right? Basically, it makes the random quantity very close to its expectation. Right? Because I am making sure I'm taking the person who's important in drawing pictures. I'm taking the person who's important in drawing in sort of doing programming. I'm defining the sensitivity in this particular way. The next important question is that how do you calculate the sensitivity, right? Because see, I mean, again, sensitivity has to be calculated with a max of all possible queries, and I say that the infinite number of queries. So how will I do this? The point is that you don't exactly need to calculate the sensitivity. But as long as you get, you ensure that everybody's importance is at least the sensitivity score, right? Because I don't need to calculate, I don't need to know that, I don't know, Professor Singh, he draws as good as Leonardo da Vinci, right? I just need to know that he draws, I just need to know that, okay, that he draws very well, right? That's all. Sorry for picking on you. Perhaps you don't draw, but that's okay. Yeah. So this will work, and it turns out that it's easy to get this upper estimates. Right? It's possible to get this upper estimates easily. The second important point is what I mentioned, and this gets more technical. We said that we need a guarantee for all possible infinite queries. So how do I do this? Right? And I won't go into this. But this is basically what you do is that you partition the space of infinite queries, right? Using some kind of a ball structure as I have drawn out here, right? And you kind of say that, okay, that I cover the infinite space. So imagine that you're covering. You have a house with infinite imagine the floor of your house. The floor of your house has, let's say, an infinite number of atoms. But if you count the number of tiles it has, that is a finite number, let's say. Sorry, I should not really say the infinite number of atoms, so let's call that infinite, right? But the number of tiles it has is finite. Basically, you tile your house and then you ensure that you have a representation from every tile. In very plain English, that's what you need to do. And this goes into the very basics of learning theory, etc. We won't go into the details of it. The interesting part is that to apply this, you don't need to go into the details of this. The next point is the following. How do you estimate the sensitivity? How do I know, right, that one of you is good in dancing, one of you is good in programming, right? And who is good in dancing, who is good in programming? So that's what this gorilla says, right? So there are lucky ways, there are easy ways of finding it out, right? That, again, the intuition is something is similar. That suppose I don't actually give you the task to program, the task program. I just ask you to solve a problem which is very similar to that problem, to the programming problem, right? All I need to get is a very sort of bad approximation to how all of you will be doing for the programming task. A bad approximation to to all of your sort of abilities for the programming task, right? Or to bad approximation to all of your abilities for the dancing. And for that, I just give you a very simple dancing task and see how you're performing in rhythm. Basically, I get a bad approximation to this problem, and that works. That works, right? And this is known as getting a bi-criteria approximation to the. It's like saying that you get a bad approximation to k-means. Based on the bad approximation, I figure out how they perform. So let's not go into the details of it. Let me just show the. I'm doing very badly. I'm almost. This is good. So okay. So let's just see the k-means example. It's like the following. That suppose we have these points. Let's just. Do I have a picture? Okay. No, I don't have a picture. So let me draw a picture. So suppose I have the actual points. Okay. And suppose this, and I'm going to say k equal to 2, right? And so how would I get everybody's sensitivity for the k-means problem? What I say is that get some approximation c prime. So let me call these c primes. Let me call these as the these center. Suppose I put in the center 1 here, I put in the center 2 here, right? And now I assign an importance to everybody. What is the importance? And suppose I put in center 3 here. Suppose k equal to 3, because that is going to be important. Okay. So I design an importance score for everybody in the following way. Right. So one part of the importance score, right, will be the distance of everybody, right, to their closest center. For instance, this point is very far from its closest center. So I will assign it. I will sort of ensure that there is a part in the importance score that assigns for everybody's distance to its closest center. This point is close to its importance. It's sort of close to its center. So therefore, this quantity will be small. There will be another part out here that says that, okay, this point is in a cluster that's fairly small, that's kind of isolated from the rest, right? So C prime X is 1 here. So cardinality of C prime for this point is X is 1, because cardinality of C prime is the number of points in this cluster. Don't worry about this one so much. This one is more technical, right? So basically, I will kind of define importances of points based on multiple criteria and combine them. I'll say that, okay, this point, while I have a bad approximation to k-means, I can already see that even in this bad approximation, these points are isolated from the other points, come in sort of clusters that are smaller. So therefore, I need to ensure that these smaller clusters are represented, and therefore I will weigh them inversely proportional to the size of the cluster. I will have a component there, and even if this point is in a large cluster, it's pretty far off from its cluster. So therefore, its contribution is fairly large, right? And so therefore, I want to make sure that I capture that. Right? This is an intuitive way of sort of building this, and this is really the critical part in each of these problems. In each problem that you take, sort of figuring out how to sort of create the upper bounds to the sensitivities. See, the exact sensitivities we can never capture. Exact sensitivities are calculating exact sensitivities is as hard as solving the full problem. But turns out that you can sort of do the smart upper bounds on the sensitivities, and you can use the sensitivities to these upper bounds to calculate the course set. Right? And the size of the course sets will now be fairly small. In fact, it will depend on the upper bounds that you use. Right? So the better the upper bounds, the smaller the upper bounds, the smaller the size of your course set. Okay. I won't go into the details of the least square. Let me just show this to you. For the least square regression, right? For instance, there is no. So for the clustering, it was easy to see the geometry, right? Because there is this cluster here, there's a cluster there. For least square regression, the geometry is a little different, because if you remember, if you're solving ax minus b, ax minus b2 norm. There's actually a very beautiful geometrical picture. Geometrical picture is something like this. that you take the subspace spanned by the columns of A, and then you try to project B onto that subspace and find out what is the best projection of B onto that subspace. And that is what this is figuring out. Right? So it turns out that when you create the course set, right, because you don't have, you have a subsample of the rows, you don't have this exact space, you have a subsample of the rows of B, so you don't have this exact B, but you have to preserve this geometry. In some sense, you have to preserve that you will get another subspace, and this will be the span of the columns of C, right? And this will be the span of the this will be the point B tilde. And while B tilde will not be and B tilde, and you need to kind of make sure that the angle that the B tilde makes with the subspace, right, is basically close to 90 degrees and all of that. So it's a very very geometrical sort of problem. When we deal with L2 LP, right, what you need to do is that you need to do further funny things. You need to generalize the definition of orthogonal vectors. Generalize the definition of orthogonality, right, according to P norms. That's a very interesting piece of work. A little biased because we did it. Okay. So now let us go into the properties of some of them, of some course sets, and we'll have to rush through some of them. First of all, here is a very cute property. But suppose you have two different machines. Right? You have machine 1 which contains the data set P1, you have machine 2 that contains the data set P2, right? And suppose in each of these machines, right, you created a course set. So the course set is much smaller than the full data. But now suppose your boss comes to you and tell you that no, you have to create a course set of the full data. What will you do, right? Yeah, do you really have to transfer all these two into one machine and then calculate and then run the course set algorithm on the full data? The very cute thing is that you don't have to. If you have calculated the course sets on the individual machines, if you take the individual union of these course sets, that actually forms the course set on the union. That's a very beautiful strategy, because you have all heard of this Google. Google does not really have a supercomputer, right? For instance, it has 10,000 or 50,000 possibly small computers, and it distributes the data on them, right? And this is something that it can do now, right? And it does that it creates the smaller course set on each of the data, on each of these small data sets, right? And now it doesn't have to transfer all the big data from one computer to another. It just transfers the small course sets, which are much smaller than the original data, into one machine, and then that is the union of the course set. So it allows me to distribute the computation among multiple machines. There's another problem is what is known as composability, which is that suppose from P1, right, you have created one course set C1, and then you decided that no, I want a smaller course set. From C1 I calculate another course set from C2. Turns out that C2 also now is a course set on the full course set of P1 with guarantees which basically add up the two guarantees. Right? That if this is the epsilon course set here, if the delta course set here, then this is the epsilon plus delta course set out here. So the guarantee gets a little worse because you're kind of multiplying the guarantees. I don't know if I want to cover. Okay, we have 10 minutes. Okay, then that's fine. So here is another important. Here is a streaming strategy that I mentioned. Right? Now suppose you have data that's coming to you in these chunks. Data that's coming to you in these chunks. Right? So this is a chunk 1, chunk 2, chunk 3, and at any time point, right, you only have enough memory to, let's say, handle 2 of these chunks. Okay. So now what you do, right? And one nice thing you could do is that you can combine you can combine these two, create the course set. Create the course set out of these two, right? And just keep this and ditch this. Now the next time a data set comes, right? You create the course set of this and this together, right? And then ditch this. You create the course set. Next time another one comes, right? Create the course set of these two, ditch this, create the course set out here. This looks okay, right? Because you're composing course sets, right? Perhaps, see the interesting thing is that if the size of this is like 10 KB, right? At any point, you're only maintaining 10 kb. Sorry, 20 kb, let's say, because you're maintaining one data set out here and one data set out here, and then you're only maintaining 20 kb, and this could be infinite. So basically, you created a course set out of an infinite stream by only maintaining 20 kb with you. However, this is not so good, because see, remember, we said that okay, if this is guarantee epsilon, this is guarantee epsilon, this is guarantee 2 epsilon, and so this is guarantee 3 epsilon, and so this is guarantee 4 epsilon. So this looks weird, because I mean, as the guarantees, as I keep on increasing, if I do 1000 steps out here, the guarantee is like 1000 epsilon. That's a little bad, right? Because I don't know, the guarantee is increasing linearly in the number of steps. There's actually a very beautiful way of doing this. Okay, that is the mathematical statement of what I say. There's actually a beautiful way of doing this, and this is known as merge and reduce. Let me not show you the theorem. Let me not show you the sort of algorithm. You can read the algorithm. I'll just show you this in a picture. What you do, so think about it as maintaining a binary counter. You all know how you all have written programs to maintain a binary counter. So let's say we have these 4 boxes, and we'll maintain the course set, one course in each box. First time the first block of data comes, I just put it here. Next time the next block of data comes, I shift this block and then I put it here. I put the second block out here without even calculating a course. Right? Let's say these blocks are of size 10 kb. Now the third time the data comes, now comes the tricky thing. Now this is free. Now this has moved here. So therefore this was free, and so this is there. Now the third data set comes. Now what do? I mean, I could shift everybody, but I won't do that. What I'll do is that I'll combine these two. Now I'll do the course set operation. I'll create the course set out here of, I'll create the course set out here of these two, right? And now these two become free. Now I move this here, right? See, it's like, I mean, if you imagine this as a binary counter, first counter is 1, second counter is 1 0, third line is 1 1, fourth line is 1 0 0. It basically keeps on going like this, binary counters. And this is a much better property in terms of the composition. Because remember, we were saying that if you do this 1000 steps, the previous algorithm had a guarantee in which the course set factor, right, is multiplied by 1000. This has a guarantee in which the course set factor is multiplied by log of 1000, right? And which is much better, right? So if you do like 10 to the 10 steps, right, the log of this is like 10, whereas log of this is like 10 to the 10, right? So this is known as a beautiful algorithm known as merge and reduce. Okay, I won't go into it. And in theorem, what it means is that at every steps, right, you need a course set of size. You maintain a course set of size s. Your total working space is s log n, and you have a course set whose factor is only log n worse than the original problem, and therefore you need to decrease the original course set parameter by factor epsilon. But that's okay. There are other very smart smart applications of course sets for calculating low rank approximation, calculating fancy low rank approximations, etc. Won't go into details of it. Please look up all this. There are, and these are more recent work. There are course sets that people have been looking at for algorithms like finding out expectation maximization. If I figured out, if you have heard about this, we have some recent papers. I won't talk about it very much because we don't really have time. I'd rather take questions. We have some papers in which we were able to do course sets for topic modeling. If you have seen topic modeling and course sets for training neural networks, right? How do you, and these go via the routes of what is known as tensor factorization. So we've all seen matrices, which is basically a 2-dimensional thing. Tensors is that's a 3-dimensional data array. Right? If you have used TensorFlow, you've used tensors, right? And we have some course sets for that. Again, we won't go into the details of that. We don't have time. So there are course sets, more recent work, very interesting work on course sets for logistic regression, on Bayesian logistic regression, very interesting set of sort of algorithms. And more recently, right, there is some work, and we have some upcoming work out here. So in applying this course sets for reducing the size of neural networks, right? And a very interesting work by Dubey et al. Shows that you can reduce the size of, by combining course sets plus some other techniques, you can reduce the size of AlexNet, which is a very huge network, huge neural network, very famous, very network trained by Google by a factor of almost 800, more than 800, right? By, I mean, reduction in so the size of the network gets reduced by a factor 800. The inference time gets reduced by a factor of 800 by that factor, but with very similar performance. So imagine what this allows us to do, right? Now you don't have to, now for your machine learning sort of projects, you don't have to sort of writing papers, you don't have to wait for Google to give you to run this code. You can basically, I mean, it basically in some sense democratizes machine learning algorithms, right? Because now you can actually deploy some of these algorithms on your computer, maybe on the smart car, smart machines, etc. Right? Because it doesn't need to be, I mean, it doesn't really need to reach that accuracy as long as it's very close to this accuracy. There are some other very interesting applications of core sets that says that using core sets you can preserve privacy of the data, right? That you can actually, okay, you can actually take core sets and you can answer questions on the core sets, and you won't sort of give away privacy of the data in a very strict sense. There's a sense known as differential privacy, right? It says that while I mean, if you ask me questions about sort of, let's say, I mean, everybody's salary at IIT Gandhinagar, right? I will answer give you slightly wrong answers, but close enough, such that you won't be able to know whether our direct, I mean, let's say person X, I won't name a director, person X gets let's say 10 lakhs of 50 lakhs a year. You won't know if this person X is present in my I mean, you won't know whether a person in my sort of data set gets a huge amount of salary or not. You won't know whether a particular person is present in the data set or not. It's privacy in a very strict sense. Core sets can be used to preserve this kind of privacy. But this is very, very open-ended question as of now. This is very recent. So just to summarize, so I mean, core sets is you should think about it as a way to reduce the data, right, in a very smart manner. And it has come up from multiple communities, from computational geometry, machine learning. Few repeated things come up. If nothing else, that we do sampling, but we do sampling in a smart way, important sampling. We create the smartness of the sampling comes up by this iterative manner, that we create a rough approximation of what I want to optimize. Based on the rough approximation, I now sort of build a smaller data set, and on that I do more hardcore things, right? And there are a lot of very interesting non-trivial questions with practical implications. There are a lot of open questions also. In case you have any more questions, I'll be very happy to answer. One open question that we've been looking at is that there is something called, if you look at this paper, there's something called data set distillation. It basically says that CFAR 10, you can basically train the entire network by looking only at 10 images. You can create 10 images. Based on that, you can, sorry, MNIST. This is MNIST. This was the MNIST picture. MNIST, you can only take 10 images, 1 image per class. Based on that, you can basically get 94% accuracy. Right? That's an empirical way of creating this core set, right? Which, I mean, we don't understand how that is happening, but this is known as data set distillation in the literature for now. And so some of the things that we're working on, there are other very interesting questions like core sets in dynamic settings, core sets when you are changing the data, how will you change the core set, etc., etc. Can you get better guarantees than the guarantees that I showed you, etc., etc. There are some references, and I'll share the slides if you need it, and any more questions. Sorry, I rushed through it a little bit. Questions.
Participants can ask their queries. Please raise your hands. Akash, please unmute yourself and ask your question. Akash?
Hello.
Yeah, hi.
Good afternoon, sir.
Good afternoon.
So I have two questions. One is a very basic question. What is the difference between uniform sampling and random sampling?
Oh, अच्छा. Okay. The second question?
And the second question is, if I have to apply core set to a machine learning problem, how do I go about it? Is there any prerequisites, like the data should be having so many number of rows or so many number of columns?
Very good question. Very good. Very nice question. Thank you, Akash. Thank you. Okay, so first of all, what is the difference between uniform sampling and random sampling? Well, I mean, all of these are random sampling, right? I mean, sampling is random. Uniform sampling is when every point is sampled with the same probability. Right? See, I mean, we kind of use random sampling in a very generic way. We don't say what is the sampling probability, right? We assume that it's always uniform, right? And that's the distinction I wanted to make. Uniform sampling is when you're doing random sampling, but every point has the same probability of being in the of being chosen. What we talked about is importance sampling. That I mean, points have different probabilities of being chosen, right? And all the sensitivities and everything that I was talking about is how to design these probabilities. But how do you say that which point should have a higher probability, which point should have a lower probability? Is the first answer clear?
Yes, sir, very much clear.
Okay, thanks. So the second question is a very important question, very practical question, which is to say that, okay, what is the size of the, I mean, how do you know that that whether by machine learning will sort of will benefit from the size of the course set? And for that, I'll show you some, I mean, see, the point is that, I mean, you have multiple things in your machine learning problem. You possibly have n, which is the number of data points, right? And you have d, which is the dimension. Okay, so the point is that here in the, when I talked about, right, and n might be high, d might be high, both might be high, right? Here I have primarily talked about reducing n, right? You can apply the same techniques to reduce d, but I haven't really shown you those, right? Now the point is that, see, you can only reduce n to certain extent modulo d. Right? For instance, if you think about linear regression, or I mean, you can reduce n. I mean, if it's n by d, I mean, I can reduce n to be like d square, right? So if your number of data points is already of the order of d square, then there is really no point thinking about it from the course set perspective, right? Theoretically. Practically is a different question. Practically, see, I mean, here I am saying is that the course set that you have is of the size d to the p times k by 1 by epsilon square. So now theoretically, if the data set, if the number of data points is already smaller than this value, then you might then you won't get any theoretical gains. However, the point is that, and I should have really introduced some practical sort of some examples, some sort of performances here. I don't have, so I don't think, yeah, I don't have, yeah, sorry.
So,
I mean,
yeah, so I'll just intervene here. So is my interpretation correct? Let's say I have 100 dimensions and the number of rows is 1 lakh, which is 100 square.
Right.
So there is no point theoretically in applying course set, correct?
Yes.
Okay.
Yes. Theoretically, there is no point doing a course set. However, right? However, what I'll say is that practically, I mean, you should still try it and see, right? Because see that these bounds are still very theoretical, right? The practical bounds that you get, and I didn't really show those. The bounds that you get are much better than the theory result, right? And again, now I'm putting on my practitioner's hat. I mean, if you're talking about a course set, practically what you should go with is, first of all, you should try out uniform sampling, right? Because in a lot of setups, uniform sampling, because if the data set, say all of these strategies really come into useful if there is really something bad in the data. If there are some clusters which are really small, some clusters which are really far apart, but if the data set does not have that, then uniform sampling will again provide you a large fraction of the benefit. Right?
Okay.
And so you should try out, the first thing you should try out is uniform sampling. Then if you and then you try to characterize uniform sampling performance, right? So let's say you draw a plot that if I sample 10% of the data, what accuracy am I getting? If I sample 1% of the data, what accuracy am I getting? Right? You look at this plot and then you start thinking about some of these approaches, right? Trying to say that, okay, now if I start to modify uniform sampling by thinking about, okay, can I give importance to these smaller clusters? Can I give importance to these points which are outliers, right? And I mean, outliers, but not in a bad sense. Then I mean, and then can I sort of, and then you start drawing that curve again. If I sample 1%, what is the performance? If I sample 10%, what is the performance? I should really have given those pictures. Right? That's the way to practically sort of go in steps in applying courses. Any other questions or follow-up questions?
Yes, sir.
Yeah.
Khushbu, please ask your question. And sir, I would like to apologize in advance, but due to time constraints, we will be just able to, okay,
Sure.
ask one more.
Yeah, I have a short time.
Okay, sir. No problem. Khushbu, Prabhat. Prabhat, please unmute yourself. Okay, sir, I think this is it.
Okay.
And sir, I have a question. Is that in a neural network compression, just we as you have explained that we can use a core set plus quantization in the like AlexNet compression. There's also one paper you have referred like a knowledge distillation. So whether we can use a concept of core set in a data-free knowledge distillation?
I don't know what data-free knowledge distillation is. So, I mean, perhaps, I mean, and I don't think I can answer this question that easily without going into without understanding what the question is. If you can send me an email, I'll get back to you.
Yeah, sure.
So anybody, any follow-up questions, please feel free to send me an email.
Okay. I think it's completed from the participant side. Thank you, sir, for giving us your precious time. It's our honor to have you as a speaker.
Thank you. No,
it's great to hear you. It's great to hear you. We are really thankful for such an informative and nice talk on core sets and scalable machine learning. I hope all the participants have enjoyed the session and got insight on fast and scalable machine learning techniques, which are really a recent requirement of industrial as well as the academia research. So thank you, sir, for giving us a new perspective to handle the computational challenges for designing scalable machine learning and optimization problem. So yeah, since Professor Singh is not available due to the urgent meeting, so on behalf of Professor S.K. Singh and IIT BHU, we are really thankful to you. And so yeah, in near future, we are definitely looking forward for the collaborative work as well as your guidance or this type of task.
Sure.
Thank you, sir.
Thank you.